So as I said, I am Sarah Jacobson, and I teach at Williams College. I'm an environmental and behavioral economist, and this talk is just going to be about climate change economics, and we're very happy to have you all here. Um, I co-authored this slide deck with my colleagues Shana McDermott and Sharon Shoemake, who are two other environmental economists, and we had the slide deck reviewed by two different environmental economists who view themselves as being at opposite ends of the ideological spectrum. And as a result, we feel that this presentation represents the nonpartisan consensus of expert economists on things related to climate change. Of course, I am a human being, so at moments, if you ask my opinion about things, I will voice Sarah's opinion, which is not necessarily Need's opinion. In fact, Need has no opinion. That's just wanted to get those caveats out of the way. As we go along, I find that there's often a lot of great questions that come up in this talk, and so I love to get your questions. You can submit questions in the chat as they occur to you, and I will try to keep up with them as they go. I will also pause to see if people have questions, and then if there's time at the end, we'll do question answer. But sometimes I find it's easier for people to ask questions as they go. And these slides will be available on the Need website as well. So the structure of this talk is as follows. I'm going to talk to you a little bit about economics building blocks. We don't have any prerequisites for this Need course, so I want to make sure everybody's on the same page. And we're going to talk a little bit about the basics of climate change, how it affects people. We're going to talk about um, reducing emissions and climate change policy. And then we're going to talk about a specific policy and how it has been working. So just to kick things off, the economic building blocks. So when I started studying environmental economics, my mom was kind of flummoxed a little bit. She said, "What can economics have to do with the environment?" And I hope at this point I have some good answers to that question. I think that we actually can be quite helpful in thinking about this. So we are a very quantitative social science, and as such, behavior of humans and firms and other structures that humans make is at the heart of what we do. So we can think about how humans will react as climate change progresses, and we can model that and measure it. There's a lot of economists who are spending a lot of time right now thinking about measuring and quantifying the damages from climate change, as well as the costs of fighting climate change. And that's really important for reasons that we'll talk about as we go forward. And finally, because economists think about incentives and how people respond to the structures that they're in, again, we're a quantitative social science. I think that economists are very good at thinking about how policy can be designed in ways that are going to minimize overall social costs. And you'll see how that shows up in when we think about climate change. So if you know anything at all about economics, then you probably this is the thing that you know, which is that in certain very special circumstances, we don't need any kind of regulation because we will magically get to the wonderful happy place just by people making their own decisions. So if you think about a very simple transaction, let's say that I am growing apples and I'm selling you apples. If I'm the only one who feels the costs and benefits of that growing, and you're the only one that feels the costs and benefits of consuming the apple, then society can't do any better than letting you and me choose together how many apples we should be trading, because we are the ones who are best positioned to judge the benefits and costs that we are facing. And so the prediction is that we should just leave that market alone and we will get the maximum social welfare, the maximum total benefit for people in society. But a lot of situations are not like that at all. A lot of our situations affect other people. So I'm talking to you right now on a computer which is powered by electricity. That electricity is creating pollution as it is generated, and that pollution causes an externality. Some of you know the word externality. It's basically, you can think about it as a side effect that's going to hurt someone that didn't have any say in the decision that was made. Here it is, I'm choosing with the electric company how much electricity to buy from them, but there are people who are being hurt by every kilowatt hour of electricity that I consume. And those costs are not being represented in that transaction between me and the electric company. And therefore, it's kind of, you can think of it as we're shoving costs off on other people. And so things that pollute have an unfair cost advantage in that way. And as a result, essentially, because those costs aren't accounted for in the decision making, we have too much pollution that happens as a result. And so the prediction here is that we can improve welfare by intervening in a market like that, by trying to make it so that we get to the efficient amount of pollution that's just going to balance the costs and benefits of that pollution. So making it so that all of those costs and benefits are accounted for. Now, that might sound weird, costs of pollution sounds kind of straightforward, like we know pollution has a variety of harms. We'll talk about that in the context of climate change. The benefits of pollution is like a super weird phrase. And the way that I think about what that would mean is that reducing pollution is costly. And so one of the big benefits of pollution is that you don't have to incur the cost that it would take to reduce that pollution. So we're just balancing those two things when we have an efficient amount of pollution. Now, when we think about this in the context of climate change, those two things that are on the scales, reducing our greenhouse gas emissions, abating our greenhouse gas emissions is costly. But on the other hand, climate change damages, the damages caused by allowing this pollution to cause these impacts on the planet, are also very costly, and in fact more costly if we don't intervene. And so we think in classic pollution economics about just balancing these two, getting to the amount of pollution that just balances those two. Typically, the goal is not to get to zero emissions, but to get to the level that just achieves that balance. And now I'm going to take the first little moment where I step to the side and say Sarah's opinion, from having looked at the way that climate change damages have been turning out to be more than many of us had expected or predicted in terms of the science. I actually wouldn't be surprised if the efficient amount of greenhouse gas emissions really was zero at this point, but that's a more specific question, and I think the science will tell that over time. So, but going back to the sort of the big picture, most of the models that we have when we think about the costs of reducing our emissions from climate change, those are estimated to be relatively small. They say 1 to 4% of GDP. Some of you might say, well, that's a small number because that's a number, 1 to 4 small numbers out of as percentages go. Some of you might say that's actually a big number because GDP, if we're talking about global GDP, is a really big number. So in absolute terms, this is quite a big number. But what matters is that if we keep climate change to that amount, 2 degrees C, which is a common target people talk about, then we're avoiding some really big costs. And those costs are damages that are something like 7%, maybe even up to 20%. In terms of worldwide GDP. So it's definitely worth it to fight climate change. The question is just how much. I also have some slightly newer estimates, and your Zoom panel of videos might be on top of some of these. So the policies that are already out there in the world, this might surprise you. There are a bunch of climate change policies that are out there. And if people follow through on them the way that they are designed, then they should limit the warming that we would face in the planet to 2.5 degrees C versus, 5 or more degrees C, which is what it would have been without the policies that are already out there. That should yield about $900 trillion in damages, according to some newer models. And if we can keep warming below 2 degrees C, then that can get damages down to this red bar of 451 trillion. So that saves 5.2 trillion annually, or 467 trillion total, if we're talking about over time. These bars are amounts of damages over time. And if we keep the damages even lower to this 1.5 degrees C that people talk about, then we can save even more in damages. Okay, so I've said a bunch of things about the general theory of pollution economics. Any questions or thoughts that folks want to share at this point? All right. So next thing I want to talk to you about is just the basics of climate change. And when I think about climate change, I like to think about the pieces in terms of a ladder of different rungs of um, phenomenon and intervention. And so the first rung that I like to think of is emissions. So we have a certain amount of greenhouse gas emissions that are going out. We're going to talk about each of these in turn. Um, we can reduce those emissions, the next rung on the ladder, so in a place for intervention, we can reduce those, and we call that reduction mitigation or abatement. We're going to talk about abatement. Given a certain amount of end emissions that we end at after we have some emissions and then reduce them to a certain amount, there's going to be some climate change happening in the world, and we're going to be doing some adapting to that. We'll talk about this as well. And then finally, there's going to be some damages that still persist even after we have reduced our emissions and done some adaptation. So we'll talk about each of these rungs, but we're going to start out with the science of how emissions translate into climate change. So the greenhouse effect is an idea that people have talked about for many, many decades at this point. And it has to do with this lovely atmosphere that we have around the Earth, which I'm really grateful for. Because what happens is the sun is putting out solar energy, it's going through the atmosphere of the Earth, hitting the Earth, bouncing back, and some of that energy goes back out through the atmosphere all the way into space. But then because we have an atmosphere, some of that energy stays inside the atmosphere. And that's really great, because if that wasn't the case, then we would be living on a cold, dead ball, and that would be bad. So because we have an atmosphere, we have some energy that is retained that basically allows for all the kinds of life that we have on Earth. What happens when you have climate change is just basically, in the simplest terms, that gases that we emit go out into the atmosphere and they accumulate and they change that thermal balance. So they change the ratio of how much energy that's bounced off the Earth goes out into space and how much stays within the atmosphere. So everything about climate change is about increased energy retained within the atmosphere, just as it happens within a greenhouse. And different greenhouse gases, as they're called, have different amounts of hang time, different amounts of persistence in the atmosphere, but they all hang out in the atmosphere and have this impact. So we can talk a little bit about the greenhouse gases that we put out. So this is a graph from the Intergovernmental Panel on Climate Change, which is a United Nations body that reports on the scientific consensus. Your panel of videos might be on top of the key of this diagram, but the way this graph works is that on the horizontal axis you have time going back to 1990 and up to 2019. And the vertical axis is the amount of greenhouse gas emissions that were put out on the planet. And these different bars are different types of greenhouse gas. So you can see that carbon dioxide is the largest one, and carbon dioxide from fossil fuel is this big blue blob on the bottom. And you can see that that is large and growing. There's also carbon dioxide from other activities like land use. This orange bar here is methane, and then nitrous oxide and fluorinated gases are up at the top. You can see really that the reason that people talk about greenhouse gas emissions as carbon is that carbon dioxide makes up a really big chunk and methane makes up another substantial chunk, which is also carbon-based. So that's the flow of greenhouse gas emissions that we've been putting out on the planet. You can see it's been increasing over these 30 years depicted in this diagram. This is a graph that comes from the National Oceanographic and Atmospheric Administration. This is an observatory up on Mauna Loa in Hawaii. I know we have a Hawaii attendee. We have been measuring carbon dioxide concentration. So this is how much accumulates in the atmosphere there since the 50s, when people started thinking about the greenhouse gas issue and the greenhouse effect. And so you can see that our carbon dioxide concentration has increased over time, and now we are well over 440 or so as of this measurement that I just took down the other day. So the greenhouse gases accumulate in the atmosphere. Now, this other graph, I'm going to talk you through this. I know it looks like there's a lot going on, but it will all make sense in a moment as we talk through it. So this horizontal axis is time going from 2000 to 2100. So you can see it starts in the past and it heads off into the future. And in fact, these dashed lines here are projections into the future from when this was made. So this is another graph from the Intergovernmental Panel on Climate Change, that science consensus body. The vertical axis, again, is the amount of greenhouse gas emissions. So this was the stock of accumulation of greenhouse gases in the atmosphere. This is how much is flowing out each year. And so what this graph is showing is a certain amount of emissions up in the years until they did this, this exercise. And then starting at the time when they did this exercise, what they basically did was they projected forward 4 different possible futures. And these 4 different possible futures are called representative concentration pathways. And these are based on the different choices that we make as a society about how we want our emissions to evolve over time. So this gray path used to be called the business as usual path. And this is one where you can see that emissions peak pretty late in the century and kind of flatten out. And it was called business as usual because back in the day, if we didn't intervene, this is what was projected to happen. And I'll come back to that in a moment. And then you can see that there are scenarios where we flatten out earlier in this pink one, or where we start to bring emissions down in this orange one, or we bring emissions down very dramatically in this blue one. So the good piece of news, so basically, again, thinking of these as different possible futures, the good piece of news is that what used to be called the business as usual scenario, this gray path, that was associated with so much emissions growth over time, that is no longer our business as usual trajectory because a lot of climate policy has already gone into place and a lot of technology as a result has already improved. So we are not, I don't know what path we're on right now. I don't think any of us knows what path we're on. We do need more policy, most likely relative to where we are right now. But the good news is that things are not as bad in terms of emissions trajectories as they were a few years ago. This is an even newer set of estimates. So remember, the Intergovernmental Panel on Climate Change does their estimates based on the scientific consensus, and they do these reports every, 7 to 10 years, and they take a lot of time to put things together. This is a newer model, and it is projecting different pathways that we can use to converge towards the climate futures that we're looking for. And so this one looks at a business as usual from basically like a couple of years ago scenario, is this blue path, and it's projecting that emissions will actually fall, especially carbon dioxide emissions, methane emissions less quickly, and so on. We do need to reduce more quickly if we want to hit these particular climate targets that people talk about a lot of 2 degrees or 1.5 degrees of warming. That I think that reduction in emissions is something that people might not necessarily know about. All right, any questions before I move forward anymore?
Yeah, I have a quick question. So where are we today with the temperature rise? You say 1.5 is where we want to hit, or is projected, but we've seen some warming, right?
That's right. That's right. So that was a wonderful segue, and I appreciate that. So we should think about it. It's a little bit complicated to think about because you always hear, this many degrees hotter, that many degrees hotter. The sort of best way to think about it, because we know that there is a lot of fluctuation, there's variation across the globe and so on, is global average surface temperature and sort of measured over a several year window because we know there can be a lot of fluctuation. But the measurement right now is that we are at 1.29 degrees C over pre-industrial levels. And so this is a graph of global average surface temperature change from the last century's average. And this is a graph from the EPA, actually, the United States Environmental Protection Agency. And so you can see all the blue years are years that are colder than that average, and all the red years are years that are warmer than that average. And so you can see that things have been warming up pretty substantially. And so 1.29 is the current estimate of the warming that we've had so far. I think we'll talk about this when we talk about damages. But I think for me, the best way to think about the 1.5 degrees and 2 degrees targets is not that like all of a sudden you hit 1.5 degrees and something explodes, like things go really bad all of a sudden. But it's useful to have a specific target that you're shooting for sometimes when you're with policy. And every 10th of a degree of warming that we have is going to increase the damages that we face. Next, any other questions that are out there? All right. So that's the global temperatures over the last century and a half. But this is local temperatures. So you can look at your own local temperatures. If you go to Berkeley Earth, you can look in their city list and see what's going on with you. What I'm showing you right now is Massachusetts. And they compile together different temperature records. And again, your Zoom video panel might be on top of the most interesting part of this. And so you can see this record actually goes all the way back to the 1750s for Massachusetts. And you can see the temperatures are tootling along. And then in the industrial age, it's just a very clear trend upward over the years. And this stripe representation is something that some of you may have seen as well. There was a very famous cover of The Economist from some years ago where they showed this for the global temperatures. It's basically the same idea as this this graphic here, except with more gradations in terms of the colors. So blues are years where it's colder than the average, reds are years when it's warmer than the average. And so here you can really see these reds really pop out, that we've had just a lot of warmer years over time. Okay, so that's for me, I think the basis of what I like to think about when we're thinking about climate change and how it operates in terms of the science. Any questions about anything else so far? All right. So we care about climate change because climate change affects us. When I was a little kid environmentalist, I was always going around and saying how we had to save the trees and save the whales and so on. But I think environmentalists right now are really super smart because they're saying what we need to do is save the humans. And so we're going to talk first about how greenhouse gas emissions affect the planet. And then we're going to talk about how those turn into effects for human beings. So increased temperatures we've already talked about to some extent, but increased temperatures have several important knock-on effects on the physical world that we live in. Sea level rise is one of them. You probably already are thinking about sea level rise due to glacier melt and ice melt, and that certainly is a thing, but also remember that things that are warm expand, and so that's another reason for sea level rise. Increased temperatures and that sea level rise also give rise to more storm surges and more destructive storm surges. This energy, that extra energy that's retained within the atmosphere, that also changes precipitation patterns. So some places get rainier, some places get drier. But in general, places have weather that is more variable. And I know that we've seen that here where I live also. Some years we've had just very serious droughts. Some years we've had horrendous rainstorms that have destroyed the crops in summer here in Massachusetts. And so it's just been very, very highly varied from month to month and year to year, and even day to day sometimes. We're not sure about whether the climate change will cause more storms, but we do know that that increased energy inside the atmosphere, it does seem to be feeding more powerful storms, and that's something that we see in hurricane season and so on. And another sort of related phenomenon is, from our greenhouse gas emissions that's not climate change, but it is related to those greenhouse gas emissions, is that carbon dioxide molecules dissolve in the ocean, they break apart, and that yields ocean acidification. So basically, the ocean turns into a giant, very weak Coca-Cola, except without the cola, not just the bubbly part. And that has a set of impacts as well. So we care about these things again because they affect us, and this is a non-exhaustive list of ways that it affects us. Obviously, agriculture, when things are getting hotter or colder or wetter or drier, agriculture is going to be affected, especially by that variable weather. Fisheries. So here in Massachusetts, we have some cod fisheries that have migrated up the coast, and also the ocean acidification that I mentioned. It also affects the food chain for various important fish. Storm surge, as I mentioned, causes a bunch of coastal damages. Health effects are important. So we've had a lot of unfortunate illness and death as a result of temperature and drought. And that's really upsetting to see that spreading across various places. Vector-borne disease is also growing. So I know that in many parts of the US, we don't have the mosquitoes, the Aedes aegypti, that carry malaria, but those mosquitoes are moving farther and farther northward, as are other kinds of disease-bearing vectors. So a whole variety of different kinds of impacts. I won't go into detail on each of them. Wildfires is something that, again, unfortunately this year, we had some poor air quality from Canadian wildfires. We know that higher temperatures reduce productivity and increase violence. These are behavioral impacts that happen directly as a result of heat and pollution. But we also know that all of these things are going to compound each other. We might have populations moving around, and we might, as a result, have increased conflict. So there's a whole panoply, and this isn't everything. It's a whole panoply of impacts that we care about. Now, I told you before that what economists like to do is think about the right amount of pollution being the amount where we balance the costs of the damage from that pollution against the costs of fighting that pollution. You might look at this list of forms of damage, and you might say, those are, how do you even add those up and put those on a scale? Yeah, that's right. So Martha said sea rise is drowning islands causing mass migration, right? So sea level rise, that you can think of the islands being degraded and as being a form of coastal damages, but some of these islands are below sea level, right? And so we have some migration that has to result from that, or that may have to result from that. So these things are all very difficult to think about putting on the scales against the cost of abatement. So how do we do that? We have a construct that we call the social cost of carbon. So this is a policy tool created by economists to basically put dollar values on each of those damages that we expect to happen as a result of climate change, and to just add them all up. And that tells us, for every ton of greenhouse gases that we put out, how much does it hurt us? And so there was an estimate that we were using for a long time, which was about $51 per metric ton of carbon dioxide, but which, was not nothing. It was a fair amount. It was about 32. It was about, it would be equivalent, like if you were driving your car, the amount that an American average drives it, then you would be incurring about $157 in costs per year. But what's interesting is that last year, the work of economists across the country are contributing to new science on this, of measuring and estimating these damages, found that it's almost 4 times as much. So really, the costs of damages from climate change that we are already experiencing are quite high. And that justifies actually incurring a lot of cost to fight against climate change. Now, that was the 2024 EPA that adopted this result of these decades of science, saying that the social cost of carbon should be $190 right now. The current EPA has proposed the elimination of the social cost of carbon, or basically setting it to zero, which is not congruent with the work that these scholars have done over time. Any other questions or comments before? Oh, I see there's another comment. Okay. Any other questions or comments before I go forward? So this was all about the overall damages that we face, but what's important, and I think also implied by Martha's comment, is that not everybody is going to face the same damages. And so it's important that we think about how those are distributed across the planet. And so I have this example here. This is a map of projections from a lab at University of California, Berkeley, that does some really nice work modeling climate change. And what this is looking at is specifically mortality. So not all the damages from climate change, but just specifically the early deaths that will result from heat and disease and so on. And so this projection is for if in the year 2100, if we haven't fought climate change at all, what is the distribution that we expect to see? And everything that is red is seeing an increase in mortality, red or orange, and everything that is blue is seeing a decrease in mortality. And the first thing that you might say is, look at all these huge, big blue patches. Maybe we're going to be okay on average, but remember, not that many people live in these northern regions. And then if you look at all the different places where there is red, yellow, and orange, there are quite large populations in them. And in fact, what you see is that the places with the highest increases in mortality are places where there's already a lot of vulnerability. So large parts of Africa, even Australia, which is, I would say, not as vulnerable in certain ways as this, but even parts of Europe, Middle East, and this band of Asia as well, southern part of the United States, and a lot of South America. So a lot of parts of the world are going to see these increases, but these damages are not going to be borne equally across the globe. And this is just an example of how we can see that. Even within the US, the damages will not be borne equally. And so this is a map that came out from the same lab. This analysis is a couple of years old. And so I have some thoughts about it that I'll share in a moment. But what you see here is that every place that has yellow, orange, or red is a county that is expected to have positive damages, so to be hurt by climate change, while the places that have green shading are places that have negative damages. So what does it mean to have negative damages? It means that actually you benefit from climate change. And so you can see that the places that were projected to have negative damages are mostly, but not entirely, mostly the northern parts of the country. So these are places that this projection that this team did expected improved agriculture at that time. And that's why you see these benefits from climate change. And so you might say, well, it looks like a lot of the map is green, so maybe everything is okay. But if you look at the scale of the reds go much deeper. The reds go to much higher numbers. And so the amount of damages that we see concentrated in places, in many of these places are much higher population than some of these more thinly populated northern states. So, the damages will vary across the US, but overall, we do expect the US to be hurt, but especially in these regions that are going to be particularly hurt by very large temperature increases and so on. And I'll just say one other thing is that I think that their models are amazing, but I don't think that they really do a great job of representing the variability that we are now seeing with weather. So I see that my area of Massachusetts looks like it's going to come out ahead, but from the kinds of variable weather that we've seen that's been damaging literally the one thing that, climate change was supposed to benefit for us. agriculture. You know, we've had apple crops destroyed and so on. I suspect that the variability in weather kinds of knocks out a lot of these benefits that are projected here.
It looks on this graph like if the counties are small, then the borders are black, and like Georgia looks almost all black when in fact it's just a lot of counties, right?
Yeah, I think both is true. Yeah, and as a person who has tried to make maps like this, maps with stuff at the county level are quite hard to look at, in fact, especially in the in the states on the East Coast where the counties are much smaller. But they are various colors of yellow and orange. Yeah. Any other thoughts while we're here? Okay, so that is our overall damages. Now, like I said before, we have our climate change ladder. So we have our emissions, and we'll talk about abatement in a moment, that will get to a certain level of climate change. But we know that given a certain amount of changes in the environment around us, people aren't just going to sit still. People are going to respond to those changes. And so we call those reactions adaptation. Adaptation is costly action that we take to reduce the damages that we're feeling from climate change. And so we have to, when we're thinking about the cost of climate change, consider both the damages that we face and also the adaptation costs that we incur. They're both important. And we're going to talk some about some costs of adaptation that people and firms are going to be taking on their own. Some are going to be related to government involvement. So individual level adaptation can take a lot of different forms for households and firms. As individuals, certainly many of us would tend to stay inside on a day that is very hot or that has bad air as a result of, say, wildfire smoke. We do see that worldwide, a lot more people are taking on air conditioner and turning those on more often. In fact, where I live in Western Massachusetts, when we moved to town 15 years ago, the houses did not have air conditioning, and our house still doesn't have air conditioning. But it's becoming more and more difficult to get through a summer here without air conditioning. And so I think more and more places across the world are going to see air conditioning as a really important, in fact, life-saving element of living. We know that firms will also take actions to adapt as well. So there are already farmers that are choosing to plant different crops or to plant in different ways or at different times, to make their crops more resilient to what's happening with perhaps droughts, perhaps excessive rains, and so on. Businesses are also seeing their workers suffer from the effects of heat, and some of them are choosing, just as a profit maximizing choice, to provide more water and shade breaks so that their people can keep working. And people might also, as individuals, make the choice to move to a place where they face fewer damages. Right. And so Martha makes the point that air conditioning also adds to emissions and global warming. So that is very true to the extent to which electricity is powered by fossil fuels. And we'll talk more about that in just a moment. And I will say for a long time, environmental folks have resisted, and I'm going to put this in the past tense, not the current tense. For a long time, they resisted talking about climate change because, I'm sorry, talking about adaptation to climate change because there was this sense that when we talk about adaptation, we're in a sense giving in and we're saying, well, we're going to let climate change happen and we're just going to adjust around it. And because some of the adaptive approaches that we could have actually can worsen climate change. But now we're kind of in a world where climate change is already progressing, and we're already feeling all these damages. And so I think most people who have spent a lot of time with the data really think we have to do both. We have to reduce our emissions now, and we have to keep people safe now. So right now, wider deployment of air conditioning would save more lives. And I think a lot of people are willing to make that trade, especially as I'll show you what I'm going to show you about electricity. So at the public level, sometimes adaptation is appropriate because individuals and households and firms can't necessarily take care of themselves when collective action is going to be easier and less costly than people acting alone. And in certain other cases, individuals just can't do their own thing. So examples of some of these might include it is more difficult for a bunch of individuals to build seawalls and more costly for a bunch of individuals to build separate seawalls versus for a community to build one protective seawall together. And certain kinds of forms of adaptation, like building a wetland that is going to reduce coastal damages, that's not really something individuals can do. That's something a community has to do together. And then, of course, there are members of the community that are vulnerable and less able to protect themselves. So there's a bunch of physical structures that communities can make, policies that can be enacted to protect people, even including things like cooling centers that a number of cities have put in place for those who don't have air conditioning. And the biggest form of adaptation of all is planned retreat, that is moving a community. And we've done that already for a few communities in the US. So the ones that I know about are off the coasts of Louisiana and Alaska, two indigenous communities that were on low-lying coastal areas that just were considered no longer habitable. And it's a very difficult decision. Nobody wants to leave their home, but the damages that they were facing were extremely large at that point. So I see a couple questions in the chat. So there's a question from Donna about the Central Valley being light orange in California. That's right. So the places in which we see a lot of damages, we're talking about sort of reductions in county GDP. And so some of that's which is economic activity. Some of that economic activity is producing stuff that is incredibly important to the rest of us as well. And so the knock-on effects of that could be quite large. And Tanya asked about that is right. So it is true that renewable electricity also has some potential damages associated with it. It is true, but at the same, yeah. So it is definitely better than fossil fuel in terms of the total amount of damages being caused, but I totally take your point. All right, any other questions or comments that folks have before we move forward? All right. Okay, so we've talked about climate change and how it's an externality, how it's caused, and how it's expected to progress. And now what we want to talk about and how it's expected to affect us as well and how we expect to respond to it. Now what I want to talk a little bit about is how we fight climate change. So the first thing, climate change is caused by greenhouse gas emissions. So what do? We want to think about where are our greenhouse gas emissions. So it's important, though, to think about our global net emissions because that's what causes climate change. So let me break that apart to make it clear what it means. So global, I use that word because for climate change related impacts, we don't actually care where a ton of greenhouse gas is emitted. We only care how much is emitted because it goes out into the atmosphere and it has the same greenhouse effect if it is emitted in Hawaii or Mississippi or Massachusetts or Taiwan. It has the same impacts wherever it comes out in terms of climate change. Now, many of these pollutants also can hang around in the local area and have other local impacts. And so we might care about where they happen because of that. But in terms of climate impacts, we want to look at the whole globe and think about all of those emissions. Next thing is net. What do I mean by net? So net, we should think about gross emissions as what are the emissions that are coming up out of our sources. And so that is going to be fossil fuel burning, all of these other things that are going to be spitting out these gases that we talked about before, minus the sinks. And so sinks basically pull carbon dioxide out of the air. So there's a bunch of natural ones. You already know about forests. You may or may not know that oceans also sink up carbon dioxide. But if you remember a few minutes ago, I told you about the fact that carbon dioxide molecules can break apart in the ocean, and we have acidification as a result of that. That's carbon dioxide going into the ocean. So these sinks that are naturally existing, they're there. We can augment these sinks. We can plant more trees. There are other things that we can do to try to sink some of our greenhouse gases, but from the estimates that I've seen, really kind of the game we're in is about trying to protect the sinks that we already have and trying to reduce the sources that we have. Because if you remember back to that graph from the IPCC of the different sources of greenhouse gas emissions, the different gases, there was just a ton that was from fossil fuels, and there's no way we can make that up in forests. Okay, so that's in thinking about global net emissions. Where are those emissions coming from? So first, let's think about it geographically. And so this is a set of graphs that I took from the New York Times a few years ago. They did this set of nice infographics. You can see it goes over time from 1850 to 2020. And the vertical axis is flow of greenhouse gases. Specifically, they're calling it carbon dioxide, but we're talking about greenhouse gases. So how much is going out in each year? And the yellowy orangey countries are Western countries, high income developed countries, and the bluey purple ones are other countries. And you can see that for a long part of history, it was the Western countries almost entirely putting out emissions, and then it was mostly the Western countries putting out emissions. And then you can see in the last couple of decades, China really expanded. So the US for a long time was the #1 emitter in any given year of greenhouse gases, but then China overtook the US in terms of emissions per year. So the thing to remember, though, is that greenhouse gases persist in the atmosphere for periods of time, for long periods of time. So how should we think about overall contributions? Well, the New York Times then broke the stock of how much emissions have been put out over history in halves, and one half was put out by 23 rich developed countries, and the US is half of that. So the US is basically a quarter of historical emissions on the planet. And then the other half all comes from 150 other countries, right? So you can see that China is the biggest block here also, but it still is significantly less than the US. Russia is also a big block, and so on. But another but, you may know this, but it's a lot of people in China. US has a lot of people, China has a lot of people. So if we think about this in terms of adjusting for how many people are in the country, then we see a different story again. So this is a graph that's from the Intergovernmental Panel on Climate Change again. And the horizontal axis, you can see this is a set of bars, and the width of each bar is the population of a region in terms of millions. And so each bar represents a region, and its width is population. The height of each bar is its greenhouse gas emissions per capita. And you can see that North America, #1, we win hands down. So we have the highest per capita emissions. And you can see that China belongs in this Eastern Asia block. You can see their block is very wide because it's a very large population, but at the same time, the per capita emissions are nowhere near as high as ours. So that's just if we want to think about sort of, I don't know if you want to think about it in terms of responsibility or in terms of targeting. I think they're both interesting ways to think about where our emissions are coming from. So, now I want to think about greenhouse gas emissions in the United States. So this is a graph from the United States Energy Information Agency, or is it the Environmental Protection Agency? I've forgotten. I grabbed this graph myself and I've already forgotten. So this graph goes from 1990 to 2023. And it's tracing emissions by sector over time. And so you can see, and the emissions are in, the same sort of flow of emissions amount per year. And so you can see that for a long time, electric power was our biggest emitter of greenhouse gases. Then you can see that transportation increased and transportation came to be above electric power, and industry sort of slowly falling, and agriculture, commercial, and residential are low and relatively flat down here at the bottom. So this is what things have looked like over time. And you might be surprised to know that US emissions have fallen over time. And a lot of it has to do with the switch from coal to natural gas in the electric sector. I think that's a very large portion of it. So that's what our emissions have looked like over time. But now electricity will become increasingly important for a number of reasons. So we already talked about forms of adaptation that are going to require electricity, like air conditioning. But perhaps even more important, forms of abatement are going to require electricity. So for example, my husband and I, just last year, we bought our first electric vehicle, right? So we're trading from a car that's powered by fossil fuels, gasoline, to a car that's powered by electricity. And that electricity, where is that electricity coming from? So where that electricity is coming from is this sort of a mix. And so a lot of the different ways that we have to decarbonize transportation and industry and so on have to do with electrification. So let's look at our sources of electricity. This is a graph from the Energy Information Administration of the United States. The horizontal axis is time going from 2000 up to 2023, and the vertical axis is how much electricity comes from each source. And so you can see, I think the most striking thing is the thing that I mentioned to you a minute ago, is that coal has dropped tremendously and natural gas has expanded in that time. Many of you know about the fracking revolution, and this is a big part of that. Natural gas emits less greenhouse gas per unit of energy than coal. But the other thing to notice is how much renewables have expanded over this time. So renewables, so I started teaching environmental economics in 2010, and I remember renewables were maybe 8% of our energy at that time, and they have more than doubled since then. And they've just been growing faster than anybody thought. And of course, nuclear is sort of trundling along in a very constant way. So that's the last 25 years. Now the projections, go
Can I
ahead.
just say, in that last graph, it looks like our total production has only gone up from 3,700 or so, or 3,800 to about 4,000 in 20 years, total energy production. That's pretty surprising to me.
Yeah, it is. And I'm actually looking at this graph and I'm thinking, how do these compare to each other? So if you look at this graph, it actually shows, I'm sorry, this is just emissions. This is not amount of electricity, right? So two things are happening at once in the energy space here. One is you have increasing demand and a slowly increasing population, not a really fast increasing population, but increasing demand because, we just have more economic activity. But then the other thing that happens is that energy efficiency improves, right? And so they just happen to be counterbalancing themselves over time as we've gone along. Yes, so oil, good question, Martha. This is electricity. And so electricity, we're not using oil for that, but the oil is going to be showing up in transportation here. Some of it we're going to be using in diesel for industry and in other uses over here, but most of the oil is going into transport. So okay, so that was the past of our energy and our electricity. Now let's look at the future. Now I know this graph is not great to look at. This is from the Energy Information Administration, but I'm going to talk you through it. This is projections forward from that they made last year or so. And the top line here, so this is starting at 2024 up to 2050. The top line here is total electricity. So they actually are projecting that we would increase our use of electricity over the next 25 years, unlike the preceding. But what they are projecting is that that big increase is coming from this light blue line, which is renewable energy. So they are projecting, and they have always been behind in projecting growth in renewables. And they are finally projecting that renewables are just going to keep growing gangbusters. And they are projecting that coal is going to drop off in the next couple of decades. And even that natural gas is going to decline, not to zero, but decline some. So these are the projections that we have, which I think to me is somewhat promising. Okay. Any other questions or comments before I go for farther forward? Okay. So we talked about where the emissions come from in terms of geography and sector. And so remember what we're talking about is trying to reduce our emissions so that we can reduce the overall costs that society is suffering from climate change. And so the way economists conceptualize this is that, well, what we should try to do is we should try to cut the emissions as cheaply as we can do and just like hack away at the cheapest emissions reductions opportunities. And so the concept is we line up all the possible ways of reducing our emissions. We figure out how much each has the capacity to reduce our emissions, how much does each cost per unit of emissions reduction. We line them up from cheapest to costliest, and we just bang out the cheapest ones first. And I'm going to show you a graph, which is an example of trying to do exactly that. It's an old graph, and so I don't want you to get too wedded to it, but it's going to show you the shape. And then I'm going to show you, excuse me, a newer graph that has good data in it. So this is a graph that some of you might have seen called the McKinsey curve. It is old, and it's made by a consulting agency, not by, bazillions or dozens or hundreds of experts from climate science. But this is this idea where we have a horizontal axis of abatement potential. Each bar is an abatement opportunity, and the height of each bar represents how much it will cost. And we have it from least costly on the left to most costly on the right. And you can see that there's a whole bunch that are expected, according to this estimation, to have a negative abatement cost. Now, again, think a negative cost, that's going to be something that would save us money to do according to these projections. Now, again, this is an old projection. I don't want you to get too wedded to it. What I want to instead show you is something that is maybe a little bit harder to look at, but is much more up to date. This is from again, from the Intergovernmental Panel on Climate Change, putting together consensus estimates of the different ways we can reduce our emissions and how much they cost. And they've broken it down by sector. So on this page, I have energy. This block you can think of as being land use and buildings. And then on the next page, I'll show you transportation, industry, and other. And then each block has a bunch of mitigation opportunities, and each mitigation opportunity has a length that represents how much scope it has to reduce our emissions, according to these studies, and colors that represent how costly or expensive it is. And the blue, that represents opportunities that are right now in the money. So these are things that we should be able to do right now without any subsidies. It's worth it to make these investments right now. And in fact, if you look at these big blue chunks here, so wind energy and solar energy, they both have big blue spans to their contribution. So that means that there's a bunch of wind energy and solar energy that are right now, with the current technology and the current policies in place, in the money. There's some that are more expensive to do, that are not worthwhile to do in terms of expenditures, like relative to fossil fuel energy. But there's a whole bunch that is, and I think that's why you see so much solar and wind that have been going up, is that it's just financially worth it right now, not even thinking about the environment. But there's a lot of scope to expand solar and wind even beyond that. So, we should expect these opportunities to continue to be taken advantage of worldwide. There are other opportunities that are out there that are widespread that are more expensive. So many of the opportunities that relate to land use have a lot of potential, but are projected to be relatively expensive. Some things related to buildings. So I mentioned a minute ago in response to Stan's question, energy efficiency. So you can see efficient lighting appliances. This is something that is seen to be in the money right now, as well as avoided demand for energy services, which is basically like using less energy. Those things are in the money right now, but their scope to further reduce emissions is not estimated to be very high, according to the set of studies that went into this. And then you can see again, transportation has a lot of opportunities in terms of fuel efficiency, but the scope of them individually is not that high, but it might make sense for us to take advantage of many of them right now. So this is where the science has us on abatement costs right now. Any questions or thoughts about this before I move forward? Okay, so these costs can be quite complicated to think about for a number of reasons. Well, first, it's just hard to estimate them. Um, but second, even if we're able to estimate what the costs are right now, it can be quite difficult to project into the future because new technology costs can vary quite a bit. They depend on the choices that we're making right now, such as research and development investments, such as infrastructure investment. But they're also just very difficult to see. I think you probably heard me mention before that renewables have been under-predicted by the US Energy Information Agency for the whole time that I've been an economist. They've always been way lowballing the amount of renewable energy that will be generated in future years. And I think it's just because it's a really difficult thing to project. So these things are very difficult. But, thinking about the fact that these investments can really change the cost curve of past and the future, I think that's a really important thing for us to think about when we're thinking about policy. Another very important thing is that it can be pretty cheap to put in another solar array or another wind farm in terms of the cost per megawatt hours. But the problem with solar and wind is that they are intermittent. Now the good news is there's a lot of battery technology that has been developed, and there's more and more battery technology that's actually being deployed in the world right now. So battery arrays are going in various places, and people are working on making batteries more and more efficient. So this problem of 5 or 10 years ago is something that science is actually overcoming based on a lot of investment and efforts that people have put in place. There's one more pair of things that I always like to talk about when I talk about abatement, and those are geoengineering and carbon capture. Um, and there are ways that people sometimes will think about fighting climate change, but without reducing emissions. And so they're different from each other, but they both essentially do that. Carbon capture is the more straightforward of them. And some of you may have heard of carbon capture utilization, or carbon capture utilization and storage. And it's more or less what it sounds like. So these greenhouse gas emissions that are going out, you basically grab them. So you have some kind of filter out there that catches emissions before they go out, or you have some kind of device like a tower that sort of sucks them out of the air before they get into the atmosphere. And so these greenhouse gases, including carbon dioxide, can then be stored away somewhere. So I've heard designs where they're talking about storing them in old oil wells. And sometimes they talk about utilizing them. So you can also compress them into bricks, and then maybe you can do something with those bricks, or you can utilize that pressure. Those of you that made comments about the air conditioner, you're going to love this one. If you store these greenhouse gas emissions in an old oil well, what do you get? You get more pressure in that oil well. And what do you get out of the oil well? More oil. So that is a interesting irony there. So this is something that is right now possible, but expensive, right? So you see some boutique things out there, but if you hear people talking about clean coal, this is how you get clean coal, in quotation marks, is this. But right now it's just expensive, and it just has not yet been proven at scale. I think at the even a little bit farther along the spectrum of this kind of thing is ideas of geoengineering, which is basically changing the earth in ways so that climate change won't hurt us so much. And so solar geoengineering, if anybody has seen the movie where the people are on the train, Snowpiercer, that's solar geoengineering gone awry. So the idea of solar geoengineering is, remember, the problem with climate change is that we're changing the thermal balance of the planet that we live on. Could we do something to change the thermal balance back? And so the idea is, why don't we put sparkly particles, like sulfur dioxide actually is a little bit reflective. So if we put some sparkly particles in the atmosphere, then less solar energy comes in the first place. And maybe overall we can get back to the thermal balance that we had before. So this is right now something that is very theoretical. I don't know that anybody has a lot of confidence that it's something that would really work, and we don't really know exactly what it would do to the planet. So right now, I'm not banking on it as a solution. I'm still thinking that we probably would be smart to just try to reduce our emissions. All right, any questions before I dive into policy? Great. Okay, so we can take the policies for addressing emissions, for reducing our emissions, and divide them into two categories. So I'm going to talk primarily about policies that target emissions directly. You can also think about another set of policies that have other objectives that might, as a side effect, affect emissions, and I'll list some of those in a few minutes. But when we think about those policies that address emissions directly, like emissions is what they regulate, we can then divide those into two categories. And one of those categories is what we call command and control, which is kind of an old-fashioned form of regulation. And that's where you tell a polluter exactly what they have to do. So you tell them either how much they have to emit or what kind of technology that they have to have. So for example, on my car, I have to have a particular kind of device to make it so that I'm not putting out so much smog, right? Every Clean Water Act discharge has a limit for every pollutant, and so on. The one that economists have been pretty excited about for a few decades is incentive-based policies, in contrast to command and control. These provide more flexibility. What they basically do is they fix that externality problem that we talked about before. So remember, the problem with pollution in terms of incentives is that I'm not bearing all the costs associated with the electricity that I'm buying to talk to you. And so I'm going to overuse dirty electricity. What happens when you use these incentive-based policies is that you basically make those costs matter again. So you put a price on emissions to level the playing field between clean and dirty activities. And you can do it by making the dirty activities cost more by way of tax or cap and trade, or you can do it by making the clean activities cost less. For example, subsidizing green energy. Economists really like these incentive-based regulations because while both forms of regulation can get to any particular emissions goal that you're interested in, just depending on how you design it, incentive-based policies can get there at lower cost, and I'll show you why. In terms of equity, so equity is about thinking about how different people are affected. Both kinds of regulation might have what we call regressive impacts, in the sense that lower income families bear a higher proportion of the costs relative to their income. Now I say that they might. We always used to say this. When I got my PhD, this was kind of accepted as a truism. But newer evidence is showing that because of the way that markets for fossil fuels work, that might not actually be the case anymore. So, but anyway, let's just assume for a minute that that is the case. They both of these might have these burdens in terms of the cost of living. But what's nice about the cap and trade and carbon tax is that they both generate revenues. And with those revenues, you can do whatever you want. You can give them back to people in general. You can give them back as a subsidy to low-income folks, and command control regulations don't. So these are a couple of reasons that we like these incentive-based regulations. I'm going to talk to you about a carbon tax and then a cap and trade. So the way a carbon tax works is that first you choose all of the activities that you want to cover, and that's typically either all of the emitters in an economy, or it is just the electricity sector. And then you set the tax level. Now, in a perfect world that will represent the social cost of polluting, what often happens is that you have your target tax, and then over some years, the tax sort of phases in so that polluters have time to adjust to it. But the goal would be to totally internalize that external cost. And then what happens when you're a polluter is that for every unit of pollution that you had been putting out, now you have to make a decision. Am I going to put out this pollution and pay the tax? Or am I going to reduce this pollution by 1 unit? Am I going to abate and pay my abatement costs? And so every polluter is then faced with this decision. And what they do is they look for places where they can reduce their emissions at a low cost. And if you remember, what I said we would want to do as a society is take advantage of the lowest cost emissions reductions opportunities we can. When we put a carbon tax in place, polluters are automatically going to do that on their own. The government doesn't have to know where the low cost reductions are available in society. The polluters work that out. So that's why this is considered to be a little bit less of a heavy-handed regulation. You can get the same reduction, but it's just going to happen most in places where the costs are lower. And that's why we say that the overall social costs are lower. Cap and trade is actually quite similar. So the way that it works is we choose the activities to be covered, and instead of setting a tax, we set a cap. So the total amount of emissions that we're going to allow to go out, and then we divide that cap amount into permits. So we cut it up into little permits. We get those permits out there into the world. We auction them out or we give them away. The way it often works is that we at first give away a lot of them, and then over time we phase in auctions, as I'll tell you about in just a minute. And it's very similar to a tax at that point, because every polluter, you have to have a permit to be able to pollute your unit of pollution. And so you are comparing what is the cost of having a permit and polluting versus what is the cost of abating. And again, you're going to look for the cheapest ways to reduce your emissions. And we will again get the lowest cost pollution reductions that we could in society. So there's other policies that are out there, as I mentioned, that will have impacts on emissions. And so research and development, I already talked about for green energy, really necessary to move those technologies forward, renewable energy mandates and energy efficiency, we talked a little bit about already, and some other things such as public transportation, grid and infrastructure and land use are relevant as well. But these are very good partners with policies that directly address emissions. All right, my last chunk is going to be about a specific policy that addresses climate change, but I want to pause again because I know I've said a bunch of things. Any more questions or comments at this point?
I have a question about why is it so difficult to set up a cap and trade system? It seems like there are a lot of problems that entities have doing that, including problems that California has right now.
Yeah, well, California is actually the example I'm about to go into. In California, I think looks like it has done pretty well over time. I actually haven't looked at what permit prices are right now. I think the biggest problem that regulators have when they're setting up and policymakers have when they're setting up a cap and trade system is largely about setting the original baseline amount, like the cap to have at the beginning. So with a cap and trade system, you typically start out with a really loose cap and then you ease in toward the cap that you want to get to. And in fact, I'll just go ahead and show you what it is, how it works for California. I'll go back in a minute and I'll show you the in-between slides. But they projected that over time, this is from 2015 to 2030, you can see that they projected business as usual emissions would decline at this low rate, and then they wanted the cap to decline over time. So the problem is, if your original estimate of your business as usual emissions is too high, then you're going to basically be putting out these permits that are worthless. And this was a big problem in the EU for a bunch of years. And what happened at that point was that countries sort of knew that the baselining for the business as usual year was coming, and they just put out a lot of emissions so that they would get a lot of permits. And then essentially the world was flooded with permits and they were basically financially worthless at that point. So I think that that's the one biggest thing. There's a couple of other features that are in there. I think economists have made a lot of tweaks to the original design of these policies to make them work a little bit better. Does that make sense?
Sort of. I don't really understand how the cap works.
Yeah, so all polluters are monitored. So we have this thing called continuous emissions monitoring system. And essentially the regulators also can detect cheaters because we can see using satellite data. We can look at emissions as well. And essentially there's just accounting that says like you have this many permits, you emitted this many units, like does it total out? And if not, then you pay a big fine. So the cap is just that the number of permits that are out there in the world is limited by in this case, the height of these bars.
Hmm.
All right, good. Other questions?
In a previous slide, you had the word CAFE, C-A-F-E.
Yeah.
There it is. CAFE fuel economy. What is
Yeah.
that?
Oh, that stands for corporate average fuel economy.
Thank you.
So
Okay.
yeah, so it's just what the US fuel economy standards have been called for some decades, which were increased dramatically under Barack Obama, and then we're going to increase again, but we'll see what happens. Other questions or comments? All right. So there's a lot of policies in place all over the world already. This is a map just of the incentive-based policies that economists love so much. And so you can see that, and if you ever want to look at the policies, you can actually just Google World Bank Carbon Pricing Dashboard. You can click on any of these and see what's going on. So you can see that there's a policy in the Northeast where I live, which we affectionately called RGGI, the Regional Greenhouse Gas Initiative. There's one in Canada. We're going to talk about the one in California, as I told you. The EU, we've already talked about. There's a bunch going on in China and so on. So these policies are spreading, and then there's other policies that aren't even incentive-based. But to talk about California's cap and trade system, so California matters because it is large, and also it is known as a policy pioneer. So a lot of others follow where California leads. And so there's been a lot of work done on what has happened in the California system, and that has informed design of other systems. In 2006, they passed AB 32, which had a bunch of pieces to it, but the part that economists love the most is the cap and trade part. And I'm going to show you how that has played out over time. First, again, I'll point out the cap started out pretty loose, relatively close to what people would have been emitting anyway. And then polluters were eased in gradually over time to lower pollution limits. Okay, so what did this look like? So the cap and trade actually took effect in 2013, but notice in 2013 the cap was pretty loose then. So 2013 is when it actually started. This is a graph that shows activity over time. This is a graph that's from California regulator, and it goes from 2000 to 2022, and we have 3 different lines on here. The vertical axis is the change in each of the quantities since 2000. The first one I want to draw your attention to is greenhouse gas emissions. So that's this blue line here, and you can see that from 2000 to 2008, greenhouse gas emissions grew, not a ton, but they grew. Then 2008, they dropped. You may remember we had this whole financial crisis situation. And then they never quite grew again. And if you look at this line, it's continuing to decline. And then you see the COVID dip again here. And you might say, well, that's not that dramatic. But then I want you to remember that this cap started out really loose and then was tightening over time. The other thing that you should know is that California's population was growing, and with that growing population, we also had growing economic activity. So this dark gray line up here is gross state product, which is a measure of economic activity. So while that's growing, greenhouse gas emissions are dropping. Or in other words, greenhouse gas emissions per unit of economic activity is dropping even more dramatically since cap and trade went into place. And so you can think about this as either showing that greenhouse gas emissions are dropping in a quite impressive way, or showing that economic activity was not stifled as a result of this policy. Okay, so in summary, and we'll have time for questions in a minute, I just wanted to reiterate that from all the evidence that we have, we know that climate change is a real thing and it's caused by human actions, and it already has a wide array of impacts that we're feeling right now. This is a problem. While we've made substantial progress to this point, this problem is not going to solve itself. We actually do need significant policy intervention. And the sooner that we make that policy intervention, then the more damages we save ourselves. We also can do these kinds of policy interventions in ways that are cleverly designed to reduce the burden of abatement costs and policy compliance. And economists love these incentive-based policies. I think they're very good. But we also have to make sure that we think about adaptation as being something costly that people are going to be undertaking and may need help with. And damages as something that's being distributed, and we may need to support people who are bearing damages. I just wanted to briefly mention before I stop sharing my screen that we have a variety of other need topics that are available. And so we have experts on all of these topics that can give talks on them. So we hope that you'll keep your eyes peeled for other webinars offered in our series. And I want to share with you also my email address. You can always send me an email if you have questions. You can email Need. You have our email address here. And if you like the talk, then you can go to our website and submit a testimonial or become a friend of Need. So I'm going to stop sharing now, and I'm going to see if folks have questions while we're here together. Go ahead, Martha.
Thank you. In that graph about 3 or 4 back, where you saw the gross emissions per capita and the gross emissions generally and all, the actual slope of that green line did not change at 2013. It remained very constant.
Yeah. Yeah, so if you remember the graph that let us go here, you actually, if you think back to let's see, here we go. If you think back to this slide, so notice this starts in 2015, right? So 2013, you actually, you don't really expect to, you shouldn't really expect to see a discontinuity. You should expect to see things starting to drop after that, right? So you really wouldn't expect to see a great big decline. And the cap, go ahead.
You see that green line at the bottom?
Yeah.
And it has no slope at all. I mean, no slope change at all.
Yeah, yeah. So the cap is on emissions overall, not on per unit of economic activity. So I think this is where we would really expect to see that change here. And so, it's yeah, it's possibly a subtle effect. And again, if you look at 2022, we don't have all of the cap reductions that we expect to have. We're still kind of in the first 7 years or so. So it's not, it's not draconian. It's not draconian. Like, we do still have emissions that are going on there. But it is a 20% reduction in emissions since 2000, which is pretty substantial. This would have been something like an 8% reduction in emissions since 2000 that we had before it went into place. So yeah, so I think that a thing to remember with each of these policies is that we can make any of them as aggressive as we would like. So we could design a cap and trade system that had a much more quickly declining cap if we wanted to, right? Similarly, we could make the cap go all the way down to 0 by 2025 if we chose to, right? That's an option that we have. Similarly, with a tax, we can make it go as high as we want. So with any particular policy, we can design it to be as strong as we like.
Thank you.
Thank you. Any other questions or comments? Okay, so for Michelle. Yeah, so Michelle's comment about the recent dramatic changes against renewable energy. So it is, I mean, it's pretty interesting, right? Because what had first happened was sort of turning back these incentives and advances that were in the Inflation Reduction Act that would have caused renewable energy to expand more quickly. And that was unfortunate, but I think a lot of us were saying, well, a lot of these things are happening on their own. As I told you before, a lot of these technologies are now cost competitive in many places. But right now, what's happening is they're putting stops on the development of offshore wind farms that had already been contracted. And so, I think those things are in the courts. We don't know what's going to happen with them. I think a thing to remember again is that we're part of a global economy, and other places in the world are moving forward on this. And so the slower we as the US move, in certain ways we end up being left behind. In certain ways we end up suffering more and longer than we need to. But it does seem to me like the global ship of policy and technology is already turning in this direction. And what is happening right now in the US within the calendar year 2025 is just trying to push back in a way that I think is ultimately futile. I mean, is it going to hurt us in the medium term? I think so, in terms of damages and in terms of our global place. But I think in the long run, I think that we're going where we're going. But that's my thought. Other questions or comments? All right, well, let me thank you again. I appreciate your time and attention tonight. If you want to reach out, you saw my email address. You can also just Google Sarah Jacobson Williams College. I appreciate your time. I hope you have a wonderful evening, and I hope you come to more NEED talks in the future.
Thank you.
Thank you.
Thank you. Take care, everybody.
Okay, so we're gonna